everyone, welcome to coding tutorial 5 of neural networks and deep learning. My name is Everly. Um, in today's class, we're going to learn how to build a CNN model with Keras, and then after that, we will compare the speed of CPU and GPU running on the CNN model. Alright, so now let's first start with building a model. Today we are again going to use MNIST dataset. Um, it's the same as our last coding tutorial. With load data, you can load the X train, Y train, and X test, Y test. So let's start with importing the packages. First, let's import Keras, and from datasets, we can import MNIST, and then X train and Y train, X test and Y test can be acquired through MNIST load data. Alright, now we have this data. Um, for the output Y, the ground truth, just like last time, again, we're going to use two categorical to transform it into one hot encoding. So utilities, import to categorical, and then for Y, we can apply the function both train and test set. And there, we have the Y's ready. And now let's look at X. So last time we didn't talk a lot about the image data, and we simply flattened the the image 28 by 28 into one dimensional. So here today we're going to talk a little bit more about image data. So they're usually in the unsigned integer 8 um, format. We can print it out um, for the X train. Let's first make sure that the data is correct. So yeah, we have 60,000 images with 28 by 28. And then if we print the data type, it would be unsigned integer 8. And let's check out the first image. That will be 28 by 28 of matrix. So okay, so here is the values in the first data. That's an image. As you can see, the numbers are from 0 to 255, and it's you can also see this documentation. So it's an 8-bit unsigned integer from 0 to 255. That it's in total 256 different integers. That's the values for each pixel. And to do pre-processing, so this is not always necessary. You can do it, you can ignore it, but a lot of the times we normalize the data. So what we can do here is let's first import, and we can do a normalized train X data, and for X train, first assign the type from unsigned integer to float 32, and then we can normalize these numbers into numbers between 0 and 1. So we can simply divide it by 255 and then do the same for the test set. And okay, so if we run this, if we print the normalized version, then you can see now the values are all float numbers between 1 and 0. Okay, so aside from that, we need to reshape the data. Reshape for the first dimension, use the same shape, and 28 by 28 by 1. So as you can see, we are adding a final dimension here. And the reason is that um, we need a dimension to indicate the number of channels here. So the image width and height is 28 by 28. And then since this is a grayscale data set, so we only have the black and white channel, and that is one channel. But if it's a color image, then every image has 3 channels. So for this, we can run pre-processing and it is done. So now the data is reshaped into a number of data, and then 28, 28, and one channel. All right, so now let's build a model, a CNN model here. First, we need to import sequential for the model, like last time. And we need some layers. Again, dense. We're going to use a dense layer later. And for convolutional layers, there is conv 1D, 2D, and 3D. And today we're going to use this. So for conv 2D class, we can define filters. And see here, filters is an integer. It indicates the dimension of output space, and we can have kernel size, strides, and padding. So for padding, it says here that the default is valid, and valid means no padding, and you can also use same for padding evenly to left, right, or up, down. Okay, so that's conv2D, and for a convolutional, for a CNN model, we also need max polling and 2D. So there's also 1D, 2D, and 3D. And for processing image, today we're going to use two-dimensional max polling. And we also need flatten layer. So a flatten layer is for us to process the features when at the output stage. We will again use a dense layer, so flatten is before that. All right, so we can start building the CNN model with sequential and start with defining the layers. First, add a convolutional layer with, we can define the filter, the output space size, and let's do 64, and then kernel size will be, we can do 3. So when we use 3 here, it means that we're using the 3 by 3 two-dimensional kernel. And activation function, use value here, and padding, let's use same. And we need to define the input shape. That is 28 by 28 by 1. So, um, we got to add layers. So, okay, so it went through. I just want to quickly demo that if we don't have the channel dimension, that it jumps an error saying that it's received, the dimension received is incorrect. So it should receive 4 dimensions. The first one is undefined yet because it's the batch size, and then width and height, but then it's missing the channel. So in total, there should be 4 dimensions. And so we're doing this channel dimension. All right. And after convolution, add max pooling. And for max pooling, we can define the size of the pooling. So pool size is 2 by 2. And then after max pooling, we can do a second convolutional layer. And this time 32 as the size. And kernel can be again 3 by 3. And activation function. And again padding. And this time let's do strides for 2. So that's 2 by 2. And after convolution again, we should do a max pooling. And it's again 2 by 2. That's the size. And okay, so let's just do 2 convolutional layers. And then after max pooling, we can add a flatten. Just simply call flatten. And finally, it should be the output 10 for as linear, so dense layer with 10, and activation function for multi-class, it's softmax. And let's print the summary on this cell. Okay, let's take a quick look. First, we have a convolutional layer, and the output size is as we assigned 64, and then a max polling because the size is 2 by 2, so it's shrinked from 28 by 28 to 14 by 14. And then another convolutional layer, the output size is 32 here as we assigned, and another max polling, so divided by 2 again, that's the pool size. So this is the final feature we have. And before inputting it to the dense layer, we need to flatten it. So the size of the flattened output should be 3 by 3 by 32. That's the total number of values we have eventually. And then for the final layer, we define the 10 classes for output. All right, and that's all for the model. Now we can compile and train the model. So compile, we can do an optimizer. SGD, and then we can use the loss cross entropy, and then metrics would include accuracy, and then run train the model. History is CNN model train with the train data standard, and then Y, the label, and batch size for the 64, and let's run 5 epochs. And with that, we train the model. So let's quickly evaluate the score of the model. Should be evaluate the X test and Y test. X with stand, and so with that, we can print the evaluation result with loss and accuracy. So test loss. That will be score the first return and score the second return. All right, now run this cell. So the model is training right now, and while it's doing that, we can again extract the history from what's returned from model fit. And let's use this history to plot accuracy and loss. Again, import plot. And this will be quick, just quickly demonstrating plotting so you get familiar with it. Plotting is pretty helpful in terms of running and evaluating the model. So let's print out my CNN model accuracy and plot the history accuracy. And then for Y label, it should be the accuracy. And the X label should be epoch. And we can do, oops, we can do the similar plot for loss. All right. Okay. The model is training pretty slow, so let me stop it right now. Um, so today we're going to experience GPU runtime, and you can go to change runtime type and then select GPU. Okay, save it. All right, so after you change it, um, the the cells you have run will be lost, so we can rerun everything quickly. All right, now it's training much faster. So after that, we can plot the results. So just 5 epochs. And then alright, sorry for the wait. Now we have the plots ready. Accuracy and loss. It looks like it's converging, but can still be more converged. So 5 epochs might not be enough for this model. But that's fine. You can run your own model. Just change some parameters and test it out. Um, okay, so that's for building a CNN model. Now with this model, let's quickly um, evaluate the speed here. So we were using GPU. So let's first test GPU. Import time, and for training the model, we can copy this line over. So before running this line, we can have a timestamp here. And after running, we can again have a timestamp here. And then uh, the minutes it took to run it would be end minus start. And then that's seconds, so divide by 60. So print CNN model total training time with GPU is um, all right. So let's just run 1 epoch here and let it train. So we can copy this over for CPU version. All right, so for GPU, it took 0.071 minutes to run one epoch. And now let's change the runtime back to CPU. And for this cell, we can run CPU and start from the beginning. All right, so it starts training. As you can see, it's running much slower. And then after it's done running this epoch, we can compare this difference between CPU and GPU. And you can also try running a DNN model to see if the difference is still this huge. So with that, uh, the above is today's coding tutorial. As you can see here, the time for running for training is there's a huge difference. And for today's coding tutorial, we learned how to build a CNN model with the convolutional layers, max fooling layers, and flattening. And if you have any questions, you're welcome to stop by my office hours or leave your questions on Piazza. So on top of today's coding tutorial, we also have a supplementary tutorial here for TensorBoard. Um, Recall that in the PyTorch tutorial, we have coded our own visualization functions for analyzing the model and its learning. And also in the past few tutorials, we've also walked through how to plot values over epochs, such as accuracy or loss, and we mainly used matplotlib for plotting. Um, so you might have noticed that it takes time to code your own visualization, but the upside is that you can always customize these visualizations to meet your own need. But in TensorFlow and Keras, there's another option for visualization, which is TensorBoard. TensorBoard is a visualization tool incorporated in the TensorFlow framework. And to visualize the model information, you can simply call this package. So now I'm going to quickly demonstrate how to use it. First of all, use the command to load the extension of TensorBoard. And then we need TensorFlow, date, time, and OS. So import these packages. Okay, and so to call the TensorBoard function in when you're training models, simply use a callback. So what we can do here is that we create this TensorBoard callback, and then we need a log directory. So let's create a directory here, that is we need a OS path, then join create logs as the folder, and then the name we can call date time. And now in the format of string, the year, the month, and date, and then the hour, minute, and second. All right, so this is going to be where the log goes to. So put this directory here, and we can also assign the frequency 1 here, and then we can run this model um, with this with fit and add uh, validation data and also the callbacks. All right, so now we can run this and it's training. And after this is done training, the log will be stored in this directory we assigned. So to show TensorBoard here, we can use TensorBoard and assign the directory logs. So this is the string of the directory we have. All right, let's run this cell. Okay, so um, so what we have here is you can see this is the directory name we assigned, and because I have previously trained another model, so now there's two. And let me just close the previous one. And this is the one that we just trained. Um, so for this directory, if you go to this files um, icon on the left, click on it, and you can see this is what we created, logs, and I have two models trained. So let's take a look at what we have here. So basically all the information we have include the parameters distribution in all layers. There's there are two convolutional layers and one dense layers. So if I click on this, here's the distribution. There's bias and there's kernel, the weights, and that's for both layers. We have these information that you can check out. And for dense layers, also we have bias and kernel distribution. And we, because we trained 5 epochs, so here's the information of 5 different epochs. So this is very convenient. You don't have to code anything for visualization. You can just use the TensorBoard function in the callback and then call it for showing on in Colab. And there's also accuracy. So for accuracy and loss, there is this smoothing function. If you move this, if you assign smoothing as 0, then it's the original value. And if you apply some smoothing, it will smooth over like over this line, and it also shows the original. So what I want to show you here is that if we are only training uh, a few epochs, this is not a big problem. But sometimes when we train many epochs and we plot everything in one graph, then the whole graph might seem a little bit messy and it's hard to keep track and see the trend. So I trained this other model that is contains about 100 epochs. And as you can see, if we apply no smoothing, um, it is harder to keep track of the trend. So this is not the best example because MNIST is a pretty easy data set, but you can still see like if we apply some smoothing over the two lines, then the trend is much easier to follow. And that's for both accuracy and loss that you can try. So that is basically all. Um, if you go to scalars, there's accuracy and loss. If you go to distributions, there is the histogram that we saw. And um, for downloading the graphs, you can downloading these pictures, you can go to, for example, Scalars and click on this show data, download links, and then you will see this icon here for download. So you can download accuracy plot and epoch plot, and you can decide um, whether you want only train to be shown or you want both train and validation, all kinds of combinations. So yeah, that's all for TensorBoard. Um, it's a pretty convenient visualization tool. So um, I provide the code here for your convenience. And that's all for this tutorial. Thank you.